This is the screencast for 4.7, example 6. We're going to do some applications of inverse trig functions. Example 6 asks us to calculate a viewing angle. Now, in my opinion, this paragraph is phrased a little bit awkwardly, and there is one tiny little word in there that makes all the difference. The bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. So we've got our playing field down here, 45 feet is the bottom, it's a 20-foot screen, so basically you're looking at a movie screen right here. As you move away from the wall, the angle formed by the screen at your eye. It's like at your eye, not with your eye, but at your eye. So in other words, the top of the screen and the bottom of the screen form an angle at your eyeball. I know that's creepy and weird, but there, eyelashes, it's pretty. So there's your eyeball and the angle of the screen with your eyeball. There's a distance from the wall at which the angle is the greatest. Greatest means we are looking for a max somewhere. What is that distance? Well, to find theta, this illustration that the book used in example 6 is a pretty good layout, although I do feel like they missed a step or two. Angle theta here, the angle that the screen makes at your eye, is theta 1 minus theta 2. So if I put theta equals theta 1, the angle from the ground to the top of the screen, minus theta 2, the angle from the ground to the bottom of the screen, I gotta come up with expressions for those angles. Well, that's where inverse trig, it works to our benefit. It seems complicated, but this is actually great, because I'm looking for the angle, theta 1, the angle whose tangent is opposite over adjacent, 65 over x. So I'm looking for the inverse tangent of 65 over x. That's theta 1. Then, to subtract theta 2, I'm looking for an angle whose tangent, opposite over adjacent, is 45 over x. So I need an angle, find the angle, inverse tangent, of 45 over x. So that's where the book comes up with that formula. Now, I have graphed this in my calculator and found a maximum at about 54, 10.5. Now I understand the question asks, what is that distance, the distance from the wall? Oh, it doesn't ask for the angle, it asks for the distance. So I have graphed graphed the function we came up with. X means the distance from the wall. We have labeled x as the distance from the wall. So the maximum occurs at 54, 10.5. So at 54 feet away from the screen, technically that's all the question is asking for, but I'm going to expand my answer a little bit just to help us get a better understanding. At 54 feet away from the screen, the angle is at a maximum of 10.5 degrees. That was the y-coordinate, the output, theta, this angle that is made at the eye. Now, the now try problem number 55 is not as complicated, which is good, but it does have a couple parts that I understand were a little bit different. I haven't really asked you that before. So 55, the Rising Hot Air Balloon. The Hot Air Balloon Festival, held each year in Phoenix, Arizona, is a popular event for photographers. Joe Silver, an award-winning photographer at the event, watches a balloon rising from ground level to a point 500 feet away. Write theta, an angle, as a function of the height of the balloon. So function at the height of the balloon means s has to be in your expression. So theta is going to be, let's see, we know the opposite and the adjacent. So the inverse tangent of s over 500. So the inverse tangent of s over 500 is theta. In other words, the tangent of theta is the opposite over hypotenuse. Now part B is the weird one. Is the change in theta greater as s changes from 10 feet to 20 feet, or as s changes from 200 feet to 210? So what I've done is I have plugged in theta of 220. So I've plugged in 20 to my function theta, 20 for s and 10 for s, and subtracted those. Then I plugged in 200 for s and 210 for s and subtracted those. The change between a distance of 20 and 10 is 1.14 radians. Oh no, it's degrees because I used degree mode. And then the change in 210 to 200 is only 0.98 degrees. Yes, I understand it is very small. When you're talking about a distance of 500 feet away, one little degree or even a little bit less than a degree will make a big gap at the end of that 500-foot stretch. So the change in theta is changing faster between 10 and 20 feet away than 200 and 210 feet away. The change in theta. Part C says, in the graph of this relationship shown here, do you think that x represents the height s and the y-axis angle theta, or the other way around? So I looked at this two different ways, and I wrote a paragraph down here to talk about that. I said, well, if theta is on the x-axis, theta can only go will go from 0 to 1500. I am not looking at 1500 degrees. That's ridiculous, because this is my x min, x max. So I have to be looking from -5 to 80 degrees. So I'm going to say my y-axis is theta just because of what my range is, or my y min and y max. Then my distance would be 0 to 1500 feet. The other way I looked at this is the change is happening faster, closer in, and then slower farther out. Now, I know it's really hard to tell the difference between a change of 1.14 and 0.98. Those slopes or changes look very close. But I can see as a general pattern, this function is changing slower as the farther distance I go. So that would make sense if I were looking at this function. So I have shown you two paragraphs of how I would have explained either one of those theories. Feel free to pause and look at those.